Hello again, guys. Welcome to lecture 6 of our lecture series, Chemistry for Engineers. Today, our topic will be on quantum chemistry of atoms. This lecture will be delivered in 3 parts because it's pretty long. Our objectives for today will be understanding various light sources. And as we should already know, light comes in waves. It comes in the form of radio wave, microwave, gamma rays, UV or ultraviolet light, which we know from the sun. Also invisible light, which we can relate to the electromagnetic spectrum. That's all we can see, which means that most of the light that exists we can't see. Light has been described historically as waves traveling through space, and properties of this wave include frequency, wavelength, amplitude, and these are all a part of the electromagnetic spectrum. So because wave comes in cycles, frequency is the number of complete cycle of the wave. In essence, frequency is velocity divided by wavelength. Wavelength is the distance between the bonding points on the wave, which is also the speed of light divided by frequency. In the wave model of light, amplitude determines the brightness of the light. The unit of frequency is hertz, and we'll eventually see that frequency and wavelength are inversely proportional. The shorter the wave, the higher the frequency. Speed of light is measured at 3.0 or 2.997 times 10 to the 8 meters per second. 3.0 times 10 to the 8 meters per second, 300 million meters per second, or the speed limit of the universe. Photoelectric effect describes the behavior of electron when interacting with light waves. So say for example you have a piece of metal interacting with light wave, or you basically shine some light on this metal. Depending on the frequency, this will result in an electron being ejected from the surface of the metal. So basically, depending on the frequency of light when interacting with an object or an atom, it basically results in the ejection of energy in the form of an electron. This basically leads to the photon model of light. A photon is basically a particle representing a quantum of light. Quantum meaning the smallest unit of something. So what's important here is that we understand how subatomic particles or very small particles interact with light. And we all know since the inception of this universe or time, light is the basis of everything. Planck as well as Albert Einstein proposed that energy is quantized, meaning that they can exist in the smallest form and can only be emitted or absorbed in very small units. The energy of the quantum is proportional to the frequency of the radiation, which means that frequency and energy is inversely proportional. From these small energy units, Planck derived a constant called the Planck's constant. Albert Einstein developed on Planck's equation by introducing the photon concept. So in his definition, quantized meaning that it is restricted to a value. It's restricted to a specific value. We just don't know what it is. So we looked at Bohr's model of the atom, which basically shows that an atom has its electron in circular orbit of a fixed radius. In quantum mechanical model, electrons are viewed as waves orbiting the nucleus. The evolution of quantum mechanics shows us that these electrons orbit the nucleus in the form of waves, just like light waves. So I guess we should understand that there is something more about waves. Waves from the light of the sun, waves from the ocean, sound wave, radio wave. So because the atom when interacting with radiation can emit photon or interacts with photon, this basically results in the atomic spectra. On the quantum scale, we have waves, atomic waves that are emitted from photon, which also give an atomic spectra. We can understand how atoms interact with light by understanding photon. Electrons in an atom can occupy a limited number of energy levels, and as we mentioned before, because they can occupy a certain energy level, they are said to be quantized. This basically gives rise to the quantum mechanical model of atoms, which basically gives mathematical calculation for waves. This also gives rise to orbitals, which gives us a bit more understanding of the atomic size or the size of the atom, and shape, which is derived from quantum numbers. This also led to the concept of electron configuration. This concept of electron configuration also allowed us to understand atomic bond or chemical bond. So in essence, these energy levels assisted us to understand how photons are emitted or absorbed as a result of interacting with waves, and with the ability to formulate a quantitative measure allowed us to hypothesize many things. So we spoke about orbitals in the form of waves. Electron configuration gives us a basic understanding of the distribution of the electron in the form of wave. So it basically looks at the probability of finding the electron in waves at a different region or a location around the nucleus. So this is a model that was derived from the quantum principle of electron or quantum mechanics, and for now gives us the closest possible measure as to where to find the electron. For the atomic radius, it's important for us to know that the size of the atom is largely dependent on the valence electron, or the electrons that occupy the outermost orbital. The more electrons you have, the higher the nuclear charge. Remember that the nucleus comprises of the proton and neutron. The proton is positively charged, the neutron is neutral, the electrons are negatively charged. So because the electrons are negatively charged, it basically creates an attractive force towards the nucleus. This basically creates a force that pulls the negatively charged electrons towards the positively charged nucleus and results in a force or an attraction that automatically results in a decrease in the size of the atom. The more electrons the atoms contain, the smaller the atom will be. So remember that we say that the electron surrounds the atom not in orbit but in the form of orbitals or wave. And there's also energy level where the atoms move from one energy level to the next based on interacting with photons, based on interacting with light waves. For an electron to move between energy level or a different space around its orbit or within the orbital, this basically will require energy. Ionization energy is the energy that is required for the electron to move from one energy level to the next. So the electron affinity of the atom is defined as the energy released when an electron attaches to a neutral atom. Because remember, in order for electron to move from various energy levels around the nucleus, ionization energy is required. In order for the electron to release energy to an atom or molecule, electron affinity is required. We will be looking at fluorescent light, which was created from the metal tungsten. The production of light is highly dependent on electron configuration of various gases. And in our last lecture, we looked at the chemistry of gases. We will eventually see that most of our fluorescent light exists due to gases such as argon, krypton. We also said that the electron basically does not exist in an orbit around the nucleus of the atom. It basically exists in the form of waves. So this would be the nucleus, and here you can see the probability of finding the electron at a given location or given space in time. These small dots would represent the probability of finding an electron at each given point, but the reality is the electron exists entirely in what we can process or understand as a wave. So basically, where you find the electron around the orbital, it's uncertain. And this leads us to the uncertainty principle, which means that nothing in life is certain. The location and the momentum of the electron is uncertain. The best we have for now is Schrodinger's equation, which basically gives us probability of finding the electron at a given location in time, which means that for now, they live in a cloud of probability. From the quantum mechanical principle, quantum numbers were derived for different energy levels. So for example, N1 would be designated somewhere here that would indicate that the electron is closest to the nucleus and exists in a lower energy state. Electrons further away from the nucleus exist in a higher energy state, which is why the more electron contained in the wave of orbital, the smaller the atom, because this basically leads to a high force of attraction towards the nucleus, where a negative charge is attracted to a positive charge. So there are N1 energy level, N2 energy level, N3 energy level, and so on. The quantum principle also gave us different shapes relative to the orbitals. This is designated S, P, D, F. The S orbital looks like a sphere, and it's also the first energy level that only admits 2 electrons. The P orbital shapes like a dumbbell, and it usually exists at energy level number 2. 2s and P are possible. The d orbital is like a clover leaf and exists at energy level 3 as s, p, d, and so on. So here we can see a periodic table with electron configuration as well. So hydrogen and helium, their electron configuration is 1s1, 1s2. This means that the N1 shell is filled. These elements make up the first 2 rows of the periodic table, and if you're counting, you would see that the elements are actually in perfect order. Hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron is 5, carbon is 6, and so on. So the second row, these are all 1s orbitals, all these respective number of electrons in their outermost shell or in the outermost orbital. So this means that 2p subshell is being occupied with electron. Boron, carbon, nitrogen, oxygen, fluorine, neon are actually grouped together, where the 2p subshell is being occupied. Instead of filling the 3d, these electron goes to the 4s subshell. The 3d subshell is filled with up to 10 electrons. So this explains why there are 10 elements in the middle of the periodic table. So the first 2 columns are where the s subshells are being occupied. Here we call this the S block. To the right we have the P block where all 6 columns are. The D block is the middle 10 columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, where the F block, as we've mentioned before, are where we find the actinides and the lanthanides. So again we have the S block, D block, P block, F block. So as we've mentioned before, you have various sources of light. Every light bulb operates on the same principle. Electricity is supplied to excite a substance, and that excitation gives rise to light. So the excitation process depends on the type of bulb. The filament in a standard incandescent light bulb is a very thin tungsten wire. So in the process of producing light, tungsten is heated until it's hot and it emits visible light. So basically, the heat of the wire will determine the color of the light emitted. So here we can see an incandescent light where we have the tungsten filament. This can also be molybdenum, as we know from our periodic table. There's also copper as well, nickel, iron. There's also a lead wire. So here we can see the countless amount of elements. We already have 5 elements from the periodic table that is contributing to light in the case of an incandescent light. This basically shows the fluorescent lamp, which also use elements such as mercury, argon gas, as well as phosphor coating, and you'll eventually see that this phosphor coating will help to produce light. And here we show the importance of other gases as well in the production of light, such as helium, neon, argon, krypton, xenon. And this picture shows the filament of the incandescent light. Tungsten wire is thin, so it heats up very quickly. Specific color of light is related to its temperature. Dull red color color of the iron suggests that it is warm and not hot, and the move towards brighter color of tungsten filament suggests higher temperatures. So basically, when it is warm, it is red, and as it moves to higher temperatures, so around here is like 3000 degrees Kelvin, you see where the color changes as a result of an increase in temperature. So the progression of the color is similar to the colors of the rainbow. So as we mentioned before, the tungsten filament is very thin. In a typical 60-watt bulb, it is 0.01 inch. It would be about 6.5 feet long if uncoiled, and when the bulb is lit, the filament temperature reaches about 4000 degrees Fahrenheit. And here we can see the different colors that are emitted due to temperature or a change in temperature. Well, here candlelight it burns at around 1900 degrees Kelvin, and you get this form of yellow light. At high pressure, sodium lamp will produce this color around 2200 Kelvin. Halogen incandescent light heats up 3000 Kelvin. This is basically direct light from the sun that would go up to 4800 Kelvin to produce this color for us to interpret visibly. Fluorescent lights operate differently. Instead of heating a metal, an arc of electricity travels through gas. So the arc occurs when electricity passes through a medium that does not conduct current very well. The discharge of a static electricity that sometimes occur when you touch a light switch provides a painful personal example of an electric arc. So here we can see specific atoms such as mercury interacting with electricity to become excited. And here we have argon gas and mercury vapor. So we see where argon is important in the production of fluorescent light, or various gases are also important as well. And eventually we will see that the phosphor coating is what is responsible for the actual production of the visible light that you see. Light interacts with the material. Phosphor, as we've said before, coats the inside of the fluorescent tube. This phosphor then emits many colors, giving rise to what we perceive as white light coming from that bulb. So here we can see the cathode, which is a negatively charged electrode by which the electrons enter. The electron flow towards the mercury atoms, where mercury and argon gas interacts with phosphor, then produce the visible light that we see. LED, or light emitting diode, uses semiconductor. And as we should know, the semiconductors from the periodic table include silicon, germanium, selenium, gallium. So when a voltage is applied to the LED, the electrons from this layer, or the N layer, start moving toward P layer. So upon reaching this layer, the electrons will fall into a hole. Falling into a hole, they will lose photon in the process. And as we should know, photon will basically emit light. The light that our eyes can detect comprise only a small portion of the possible electromagnetic spectrum and accounts for only a small part of the emission of most of light bulbs. Other familiar forms of electromagnetic radiation include radio wave, which comes in the form of AM, FM, TV, radar, infrared, ultraviolet rays, X-rays, gamma rays, as well as microwave. The visible light that we can see ranges from 400 to 700 nanometer and is depicted here as the colors of the rainbows that we can see. These include red, orange, yellow, green, blue, violet, and beside violet we have UV light, which we can't see. From gamma rays to X-ray to UV rays, there's an increase in wavelength towards this direction. We can also see that there's also an increase in energy from this direction. Radio waves have the longest wave, followed by microwave, that is not depicted here, followed by infrared rays, UV rays, X-ray, gamma ray. And let's not forget cosmic radiation, or cosmic rays. Where there's increase in energy, there's also an increase in frequency. Historically, light has been described as a wave traveling through space. One component is an electric field and the other is magnetic field. Here we have the temperature of the objects at which the radiation radiation is most intense, and this basically goes from 1 Kelvin, which is negative 272 degrees Celsius, all the way to 10 million Kelvin. The features of light that we can appreciate, we describe as the properties of the wave. Frequency, the amplitude, the wavelengths, velocity are all properties of waves, or the light waves that we can observe. The wavelength of any wave is a distance between corresponding points on adjacent wave, is measured in units of length. So basically, the wavelength is defined as the distance between the peaks. So here we have the crest of the wave. So to find the wavelength of any given wave or part of the wave of light that you see, it would basically be the speed of light divided by the frequency. So here we have lambda equals v, or velocity, which is also in the speed of light divided by frequency. Speed of light is c equals 3 times 10 to the 8 meters per second. So as we said before, the amplitude is the size or height of the wave. The frequency is the number of complete cycles of the wave passing at a given point per second. Frequency is designated v, so this is Greek, is designated ni. We'll use this interchangeably with f. Frequency is measured in hertz. Frequency and wavelengths are not independent of one another. So the higher the frequency, the shorter the wavelength, the larger the amplitude. The lower the frequency, the lower the wavelength, the smaller the amplitude. And here we can see amplitude is the height of the wave. Here we have two sine waves that are shown, and as we can see, these are both different frequency as well as wavelength and amplitude. Because light has a fixed speed, its frequency and wavelength are always inversely related. Amplitude is independent of frequency. The choice of which of these waves would have larger amplitude was made arbitrarily. The speed of light in a vacuum is designated c. Why c? It is the Latin name for celeritas, meaning speed. It is measured in units of distance per time. It is a constant of nature that has been measured with impressive precision and is now defined as an exact value 2.997, or as I've written before, 3 times 10 to the 8 meters per second. Because the speed of light is a constant, the number of waves that will pass at a certain point in time will be inversely related to wavelength. Long wavelengths will have fewer cycles pass by in 1 second, so they will have a lower frequency. The relationship is expressed mathematically in equation. So basically, the speed of light is the wavelength times frequency. And of course, Einstein states that you can't separate mass from energy or light. So energy is equal to mass times the speed of light squared, because light is the basis of energy. So the equation for wavelengths again is velocity. This is a symbol for wavelength. Velocity divided by frequency. If we want to describe the detailed shape of a wave, we need to write a mathematical equation for it. Imagine that we take a snapshot of the wave at a particular instant and picture it on an XY graph. So here we have XY graph of the electromagnetic wave. The wave originates at the X, and that would be equal to 0. The Y value would represent the height of the wave at each point. And as we said before, the height of the wave is the amplitude. So here are features of the electromagnetic wave. The wavelength is the distance between the successive crests of the wave. The frequency is the wave cycle passing through in a given period in time. The amplitude is basically the height of the wave that is measured between the crest and the midpoint of the wave. The velocity is the speed and the direction of propagation of the wave. We could write a very general equation of the wave where A is the amplitude of the wave, X is the distance from the origin. It would have units of length. So B in our equation must have units of length if we know the wavelength of the wave, and we could read all the graphs graph, then we can fix the value of B. In the wave model of the light, the amplitude determines the brightness of the light. The larger the amplitude of the wave, the brighter the light. And of course, because light is a wave, it's subjected to bending when it passes from one medium to another. Refraction is the bending of wave when it passes from one medium to another of different refractive index. One common manifestation of refraction is the rainbow, in which white light is separated into colors. In passing from air to water or glass, the speed of light changes and the light bends at an angle that depends on the wavelength. So refraction is basically bending of light when it passes through one medium to another at different refractive index. So when a light passes through a prism, it's separated into constituent color. The light bends at an angle that is highly dependent on the wavelength. Thus, the visible spectrum is separated into colors, and the colors are dispersed in order of their corresponding wavelengths. Because a wave-like phenomena such as refraction is common to categorize electromagnetic radiation in terms of its wavelength or frequency. So visible light is just the small portion of the entire electromagnetic spectrum that our eyes can detect. The region of the spectrum are used in many technological applications, including remote control, cell phones, wireless networks, because as we can see and as we've already know, there's radio wave, microwave, gamma rays that we can use for different purposes. The visible spectrum that we can see falls between 400 to 700 nanometers, which makes up a very tiny fraction of what we can experience. So as much as we can see all of these rays, we can measure them. And when we measure them, we express them in frequency as well as wavelengths. So here we have an example problem. So neon light emits an orange-red color glow. The light has a wavelength of 607 nanometers. What is the frequency of this light? We already know that frequency is velocity divided by wavelength, and the unit is in hertz. And of course, we can see this light of neon is probably around here. It's given in nanometers, so we should convert to meter. We have 670 nanometers times 1 meter, and we know that 1 nanometer is equivalent to 1 billionth of a meter. 1 times 10 to the 9, which basically gives us 6.7 meter times 10 to the minus 7. Now that we have the wavelength in meter, the frequency would be velocity, which is the speed of light, which is c 2.998 times 10 to the 8 meters per second, divide by 6.7 times 10 to the negative 7 meters, which basically gives us 4.5 times 10 to the 8. So this basically gives us the frequency that neon emits at a wavelength of 670 nanometers. Compared with ordinary incandescent bulbs, heat lamps are designated to emit a range of wavelengths shifted towards the infrared rays region. These bulbs appear red to our eyes because what is the visible color that is adjacent to infrared. So with this, we can assume infrared rays would be adjacent to 700 nanometers in wavelength. Our eyes cannot detect UV light, but because the lamps appear purple because the range of wavelengths they emit overlap the UV end of the visible spectrum. Microwave oven, radios, television, wireless telephones, and wireless computer networks all function by exploiting other specific region of the electromagnetic spectrum. So as we've said before, the visible light that we see, for example, from incandescent light is emitted because it is next to the infrared. When light strikes a piece of metal, this causes electrons to be ejected at the right frequency. This is basically called the photoelectric effect. So here we can see a metal plate with its electron, and then we have electromagnetic radiation with the right frequency. This basically leads to a photoelectron, or basically an electron being ejected from the surface of the metal. This is exploited in photoelectric cells. The light strikes the surface called the photocathode, and a wire, the anode, collects the emitted electron. A positive voltage applied to the anode ensures the electron travels in the desired direction. The resulting current can be measured easily and is related to the intensity of the incident light. So here the photon of sufficient energy strikes the metal surface and the electron is ejected. So the photon basically comes in the form of electromagnetic radiation of sufficient energy and frequency. It strikes the surface, which results in ejection of an electron. Ejected electrons are collected by the anode. The light will strike the surface, which is a photocathode. The electrons are collected in an anode here. A positive voltage will be applied to this anode, and this basically ensures that the electrons are collected or travel in a specific direction. And this resulting current can be measured easily and is related to the intensity of the incident light. So the wave particle duality speaks of electron being a wave and a particle. So if the metal is enclosed in a container under vacuum so that there are very few surrounding gas molecules to interfere with it, so you basically control the environment in which the metal is contained. So you have very few gas particles or molecules or electron photons from the gas particles interacting with it, then you can detect electron emitting from the metal under certain condition. The metal itself is grounded so that it does not develop a large positive charge. On this graph, it's basically a sketch that shows most observation from experiments on photoelectric effect. So here you have a threshold frequency where there is no photoelectrons emitted, but increases with increasing intensity. So for frequency greater than V0, number of electrons emitted is independent of frequency, shown here. But this increase with increase in light intensity, as you can see here. The kinetic energy of the emitted electron, on the other hand, increases linearly with the frequency. So here, if you have the electron bouncing off the metal, which would create some form of kinetic energy, there's a linear increase with frequency, as you can see for graph C, but is independent of intensity. So this basically makes it easy for us to measure how many electrons are ejected and how fast they are going. In studying the photoelectric effect, the experimenter could vary the color of the intensity of the light and see how the number of electrons emitted or their kinetic energy might be changed. And the experiment can also be repeated using different metals. So you basically get a photon laser where you pass this photon of laser light in the form of wave on the metal, and here you basically have a photoelectric photon detector that detects each particle that is ejected, and depending on the frequency, the intensity, or the kinetic energy, a certain color photon will be produced based on frequency or kinetic energy. Despite elaborate efforts to make the observation of photoelectric effect conform to existing wave concept, consistent explanation of light solely based on wave ultimately fails. So light is not generally only based on waveforms. The only way to explain all of the experimental results was invoke the notion of wave particle duality. So basically, they can't understand everything about the particle or the electron interaction with wave. In some situation, light can be described as a wave, whereas in other case, a particle description works better. So again, with photons interact with the surface in the form of radiation at different frequency will result in photoelectron or an electron being ejected. And remember that an electron being ejected will produce some form of energy, which can be measured in the form of a light wave. So the limitation of the wave-particle duality is it doesn't mean that there are two different kinds of light. It basically means that the wave as well as the particle model doesn't really give an accurate description of all the properties of light. So there's much more to it that we don't understand. And much of light being studied in the form of wave is done through the slit lamp or the slit plate experiment. So Albert Einstein proposed that light could be described as collection of packets of energy called photons. Bright lights have many photons, whereas dim light has few. The energy of a photon of light has been shown to be proportional to its frequency, leading to a simple equation. So energy equals Planck's constant times frequency, which is equal to Planck's constant times the speed of light divided by the wavelength. So Planck's constant was a constant that was derived long before now, and as we already know, the speed of light is 3 times 10 to the 8 meters per second, and this is speed of light in a vacuum. So Planck's constant times frequency is used to indicate that light is required in a photochemical reaction because energy is equal to Planck's constant times frequency. So here E represents the photon of energy and F is the frequency of light. The H term, as we said before, is the Planck's constant after the German scientist Max Planck. And for photochemical reaction to occur from the sun, the molecule is at a ground state where Planck's constant times the frequency of light determines the photochemical reaction. And because energy is also equivalent to wavelength, because remember that we said that once you have a decrease in frequency, you have a decrease in wavelength, and increase in frequency also an increase in wavelength, we can substitute the frequency in the equation for the wavelength. Energy would be Planck's constant times the speed of light divided by the wavelength. Remember that the wavelength can be represented like this as well, which is the lambda sign. All right, so here we have example problem 2. The light in a standard laser printer emits light with a wavelength of 780 nanometers. What is the energy of a photon of this light? And as we can see here, we have the equation for energy of a photon, which is E equals Planck's constant times the frequency. Planck's constant is predefined and it is 6.626 times 10 to the minus 34 joules per second, while frequency is in hertz. First, we have to convert this to meters, which we should already know. So this would be 780 nanometers times 1 divided by 1 times 10 to the 9. This is in nanometers, which basically gives us 7.8 times 10 run out of space to the minus 7, and that's in meters. So we know that energy is equal to Planck's constant, which is 6.626 times 10 to the minus 34 joules per second times the velocity, which is the speed of light, which is 2.998 or 3 times 10 to the 8. Let me see if I can just fit this in right here. And 10 to the 8. This is in meters per second as well. Remember that we have to divide this by 7.8, which basically gives us 2.547. And let's not forget, this is minus 34. So this would be 10 to the minus 19 joules. So the energy of the photon would be 2.547 times 10 to the 19 joules. So how exactly are we able to see the light? Compare that with the amount of energy emitted by an ordinary lamp. Even a modest 60-watt bulb emits 60 joules of energy each second. So the light that you're familiar with consists of vast numbers of photons. As the light gets brighter, the number of photons emitted per second increases. So this is basically showing how an atom emits light. A collision with a moving particle excites the atom. This causes an electron to jump to a higher energy level. This is basically the lowest energy level, closer to the nucleus. So this would be the first energy level. With excitation of the atom, the electron tends to move from the first energy level to the second or the third energy level. Then the electron falls back to its original energy level, releasing the extra energy in the form of a photon. And this is basically the light photon that would be emitted from the atom. Because each photon is such a small additional amount of energy, it appears to us as if the energy coming from the lamp varies continuously rather than in discrete increments of steps. Atoms and molecules are very small after all, and their typical energies are small as well. So imagine you doing this experiment by shooting a photon on a metal. This simply means that you would be supplying an amount of energy which is equivalent to Planck's constant times velocity, which is the speed of light, or 3 times 10 to the 8 to the metal, and that would be in meters per second. If this energy is enough to overcome the force that the metal atom exerts to hold on onto their electron, then when the metal absorbs the photon, it will be able to eject one electron. So if the energy is enough to overcome the force that the metal atoms exert to hold onto their electron, then when the metal absorbs the photon, it will be able to eject one electron. If the energy of the photon is smaller than the binding energy holding the electrons to the metal, then no electron can be emitted. So in essence, if small amount of energy is produced and this does not affect the binding energy of the metal, then no electron in the form of photon will be emitted. So basically an energy for an energy, or a photon for a photon. Below the threshold frequency, a photon does not have enough energy to overcome the binding energy and eject an electron. For a particular metal, the electron binding energy is fixed for any frequency above threshold frequency. For a particular metal, the threshold electron binding energy is fixed. So there has to be a frequency above threshold to affect the binding energy of the metal. So as long as the binding energy is affected, this will determine if a photon will be absorbed as well as ejected. So example 3 looks at an experiment with UV light as well as binding energy. In a photoelectric experiment, UV light with a wavelength of 337 nanometers was directed at the surface of a piece of potassium metal. The kinetic energy of the ejected electron was measured as 2.3 times 10 to the 19 joules. What is the electron binding energy for potassium? So the energy of the photon is the binding energy plus the kinetic energy. So first you'll have to find the photon energy, which we've done before. We start by converting again to meters. So that would be 337 nanometers times 1 meters divided by 10 to the 9 nanometer, which basically gives us 3.37 times 10 to the minus 7 meters. So the energy of the photon would be Planck's constant, as we already know, times the speed of light divided by the wavelength here. Remember that we can also use this symbol as well. So Planck's constant times the speed of light divided by the wavelength gives us 5.8 times 10 to the minus 19 joules. So this is basically the energy of the photon. Then use the conservation of energy relationship to find the desired binding energy. So the energy of the photon is the binding energy plus the kinetic energy. The binding energy is photon energy minus the kinetic energy. So we already know the photon energy, and we're given the kinetic energy of 2.3 times 10 to the 19 joules. So the energy of the photon minus the kinetic energy would give us the binding energy. So the binding energy is the energy that holds the nucleus together, and the frequency will determine if the binding energy will be affected in order to accept or emit a photon. Fluorescent light bulbs generally contain small amount of mercury because mercury vapor can be toxic. Breathing the gas released when a fluorescent bulb breaks can be dangerous. You really don't want to have too much mercury around. Like all elements, mercury has a characteristic way of absorbing and emitting light. And here we can see the different wavelength of mercury lamp and the colors that are emitted at different wavelengths. The particular pattern of wavelengths absorbed and emitted by mercury is called the atomic spectrum. What is most peculiar is that excited atoms of any particular element emit only specific frequency. So excited atoms will only emit specific frequency. So it's like fingerprinting. So because these frequencies tend to be well separated, the spectra are said to be discrete. This is basically just showing the intensity of a mercury emission bulb between 500 and 600 nanometers wavelength. So around this wavelength, there's a significant increase in intensity. So this is basically different from lights given off from the sun or by an incandescent bulb, which contains a continuous range of wavelength. The spectra between atoms are very discrete. They produce highly specific photons at different wavelengths, and the wavelengths that are emitted vary from element to element. So this is basically just showing the wavelengths in nanometer from the sun, which contains a continuous range of wavelengths, as opposed to a fluorescent bulb, which basically consists of wavelengths appearing between 550, 600, producing different colors. When an electric discharge is applied to a sample of hydrogen gas, H2 molecules dissociate in atoms, and those atoms then emit light. That light passes through a set of slits to create a narrow beam of light, which then passes through a prism. Prism separates the light into constituent color and shows that only a few discrete wavelengths are emitted. So this is basically again showing how discrete or highly specific each atom is when interacting or emitting or accepting a photon. So the wavelengths that are produced when absorbing or emitting a photon is highly specific for each atom. And I would assume this also has to do with the properties of what that atom is. For example, if it's basically a metal or it's a gas, we know that gases have different properties as opposed to metals, as opposed to the alkali metals or the alkali earth metals, because again, the chemical properties of each atom will also be highly dependent on their valence electron. Their valence electron will also influence types of bonding. Although data were gathered from many elements, including mercury, the spectrum of hydrogen played the most important role. Hydrogen gas can be excited in a glass tube by passing an electric arc through the tube. The energy from the arc breaks the hydrogen molecules into individual hydrogen atoms and excites some of these atoms. So the breaking of the hydrogen molecules to atom will basically emit photons highly specific to hydrogen atoms. And here you can see the specific colors that are emitted: violet, blue, green, red, at different wavelengths. So when the hydrogen atoms are excited, they emit light as they basically relaxes to the lower energy state. So the light appears blue when passed through a prism. It reveals four lines, as we've said before. So you have violet, blue, green, red. So when an atom emits light, it releases energy to the surrounding world. And this is basically conservation of energy, because the energy is transformed into a different state somewhere in the world. So when the light is emitted, the atom goes from a high energy state to a lower energy state. The emitted photons carries away the energy lost by the atom. Matter can neither be created or destroyed. It's basically just transformation in a different state. So here we can see the electron at its high energy state. When interacting with light, it basically transforms to a lower energy state. And when there is change in energy level, this causes the release of light. The fact that only a few wavelengths of light are emitted from a particular atom is direct evidence that the atom can can exist in only a few states with very specific energies. To see that this must be true, imagine what would happen if the atom could take on energy arbitrarily. So in that case, we would expect to see a continuous spectrum of wavelengths emitted because each atom could lose an arbitrary amount of energy. And moving from a higher energy state to a lower energy state causes the release of energy in the form of photon. So it basically returns it somewhere to the universe from whence it came in different colors. The first four energy levels for the hydrogen atoms are shown. The lowest energy state is labeled E1 and the higher energy states are labeled E2, 3 and 4 respectively. When a hydrogen atom undergoes a transition from E3 to E1, it emits a photon at wavelength. You just write it again so that you remember lambda at wavelength 102.6 nanometers. From E2 to E1 energy level, it emits a photon which basically gives us 102.6 nanometer wavelength. Similarly, if the atom undergoes transition from E3 to E2, it emits a photon with 656.3 nanometers wavelength. Find the wavelength of light emitted by an atom making transition from E2 to E1. So basically, you're trying to find out the wavelength that the atom or the electron emits moving from the E2 energy state to E1 energy state. So it's basically moving from a higher energy state to a lower energy state. So again, you'll have to find the energy emitted by a photon, and this would be Planck's constant again times the speed of light divided by the wavelength, and we were given two wavelengths in nanometers. So Planck's constant, which is 6.626 times 10 to the negative 34 joules times the speed of light divided by the wavelength for E3 to E1, which was given 102.6 nanometers. This times 1 times 10 to the 9 nanometers divided by a meter, because we're converting this to meter. This gives us 1.936 times 10 to the 18 joules. For the E3 to E2 transition, you basically do the same thing, where energy of the photon is Planck's constant divided by the speed of light divided by the wavelength that was given, and you convert this to meters, which gives you 3.02. So it basically gives you E3 to E2 if the electron moves from the energy level 3 to energy level 1, if it moves from energy level 3 to energy level 2. So E2 to E1 and E3 to E1 is 1.9, as we see here, times 10 to the minus 18 joules. This minus from E3 to E2, which was 3.027, and this basically gives you 1.633 times 10 to the negative 18 joules. So now we need to convert from energy to wavelength to reach the desired number. So the wavelength from 2 to 1 is going to be the same equation, Planck's constant times the speed of light divided by the wavelength of E2 to 1, which is 1.633, gives us 1.26 times 10 to the negative 7 meters. So because we know the wavelengths are most often given in nanometers, we might convert to nanometer. So this is 1.2 meter, which would be equivalent to 121.6 nanometers. So basically, to move from energy level 1 to energy level 2, it's around 122 nanometers, as you can see here. To move from energy level 1 to 3, It's basically 103, as we can see here. Bohr suggests that the nucleus of the atom is positively charged, whereas the electrons surround the nucleus have negative charge. This basically results in an opposite attraction between the electron and the nucleus, which would indicate that the electron should collapse in the positively charged nucleus. Bohr also suggested the different energy levels and shows where a photon is emitted with energy. The difference though is that Bohr suggested that the electron occupy a stable orbit from which they cannot deviate. And now we know that that's basically not true, because the electrons are more seen like wave and can be found at a given space in time that is largely unpredictable. However, without this basic or initial understanding from Bohr, we would not be able to expand on our knowledge as it relates to the electrons. So now we know that this model is not completely correct, but it's far more than most of us can contribute. It doesn't really provide a convenient way to visualize the process of exciting an atom. In any atom, the oppositely charged electron and proton attract each other. Therefore, the closer to the nucleus an electron is, the stronger the attraction and the lower the energy for an electron to move from an inner to an outer. So the ground state is basically when the electron moves closer to the nucleus. The excited state is basically when it moves from the lowest energy level. A new distribution of configuration of electron consists of a grouping that is not at the lowest possible energy and is therefore referred to as an excited state. One of the most powerful driving force in nature is a tendency to move towards states of lower energy. That's why someone would like to sleep. So an excited state of atom cannot exist indefinitely. So you cannot always be excited. The atom cannot always be excited. It has to go into a lower energy state. Most things that were created with the natural processes of nature has to go from an excited to a lower energy state. When an atom absorbs energy, its electron enters a higher energy state and the atom is said to be excited. When an atom's electron returns to a lower energy state, it will release energy in the form of electromagnetic rays or radiation. So basically, when the atom absorbs energy, it becomes excited. When it returns to a lower energy state, it releases the electron in the form of photon. So it basically releases energy in its lower energy state. It will return to the lowest energy state or ground state by emitting radiation. Both the excitation and emission process are understandable in the terms of Bohr model of the atoms. So the model is basically useful, even though some of the details are not accurate. So these are the different energy levels: N1, N2, N3, N4, N5, and 6. And as we know, this is the lower energy state. And when it goes into the lower energy state, it releases a photon. And when it absorbs an electron, it goes into a higher energy state. The idea of the electron being fixed and orbiting the nucleus in a fixed path is definitely not correct. I think that analogy was basically being made in reference to the Earth, revolving around the sun, but it played an essential role in the development of our understanding of the atomic structure. So recall that we said that all lamps are based on the principle that an excited substance can emit light as it loses energy. Now we can see that the nature of excitation largely dictates the type of bulb. This is basically a regenerative cycle with the tungsten and the halogen atoms as well as the oxygen atom. Tungsten filaments, just like an invisible material, contains many atoms, perhaps nearly a mole. An electric current passes through the wire, causes the wire's temperature to rise. Thus, the excitation process in the metal wire affects large numbers of atoms by heating them. Emission of energy from the macroscopic collection of excited atoms allow an incandescent bulb to provide us with the light we need. So as opposed to incandescent lights, fluorescent lamps are usually filled with a rare gas and small amount of mercury vapor. So remember that gases are always moving around, small particles bumping into sides of the container. In a fluorescent lamp, the atoms in the bulb are excited individually rather than collectively, and individual atoms are excited simultaneously. The behavior of any given atoms does not depend on the other atom in the tube. In a fluorescent bulb, mercury atoms are excited by an electric arc and then releases energy by emitting light. The light emitted by mercury atoms is in the ultraviolet region of the spectrum, so it cannot be the light that we see when we switch on the light. Instead, the phosphor molecule on the glass wall absorbs the emitted UV light, and another excitation and emission process takes place. So here we can see the cathode, which is a negatively charged electrode, applies current to this bulb, interacting with argon, producing mercury vapor. And so in the second step, the phosphor molecule emits light across a range of frequencies, providing light more akin to the nearly continuous light of the sun, rather than the invisible UV radiation emitted by mercury atoms. The spectrum of wavelength emitted by phosphor molecules is not quite the same as that emitted by the hot filament in an incandescent bulb. And that's why incandescent and fluorescent bulbs each have their own characteristic look. The development of light source such as the halogen lamp, the light emitting diode or LED, and laser would not have been possible without improved models of atom. The picture that emerged to enable these technological advances is the quantum mechanical model. Without quantum mechanics, you would not be talking about LED or halogen lamp. So the quantum mechanical model also assists us to describe chemical bonding more accurately, which in turn assists us in designing materials a bit more accurately. In the quantum mechanical model, electrons are viewed as waves rather than particles, and these waves are considered to be spread out or deionized through a region of space called orbitals.